Section 6.3, using elimination to solve systems. So in this section, we get another method to solve systems of linear equations. So we're asked why the substitution method that we learned in the last section would not be such a great choice to use to solve the following system. So if we think about in the substitution method, we looked through our equations and we tried to find a variable that had a coefficient of 1. And so we would look for a variable with a coefficient of 1, because then it made that variable easy to solve for. So we didn't actually have to have a variable with a coefficient of 1, it just made things easier to try to solve for one of those variables and then substitute that expression in the other equation. Well, we can see here if we try to solve for this x, in the end we're going to have to divide through by 3, which is going to introduce some fractions. 9 divides nicely by 3, but 2 does not, so we'd have 2/3. If we were to try to solve for y, eventually we'd have to divide through all of the terms by 2. And so again, 3 does not divide nicely by 2, we'd end up with a fraction 3/2, and we'd end up with a fraction of 9/2. In our other equation, the similar thing happens, because to solve for y, we'd eventually have to divide by 5, which would give us fractions. Or if we tried to solve for x, we would have to eventually divide by -3, which again, 12 divided by -3 would be -4. That'd be a nice integer value. But here, as we take 5 divided by -3, we'd end up with a fraction. So in the previous section, at least one of the variables in the system had a coefficient of 1, which made it easy to isolate one of the variables in one of the equations. Okay, we're going to look at one last method for solving a system of 2 linear equations and 2 variables. So again, if we have 2 variables, that means to solve the system, we are looking for an ordered pair, x comma y. So if there is a point that makes the system true, if ax plus by equals c and dx plus ey equals f for that particular value, okay, then it must be true that if we add these two sides of our equation, we get the same thing as when we add these two sides. Because ax plus by is equal to c, and dx plus ey is equal to, oops, overshot a bit, is equal to f. So these two quantities added together must be the same as these two quantities added together. Okay, so just as with the substitution method, we want to do something that is mathematically legal to transform our system of 2 equations in 2 variables to a single equation with just 1 variable. And then we can use our techniques from the last unit to solve for x or to solve for y, whichever the remaining variable is. So in the elimination method, we're going to make either the coefficients of x or the coefficients of y opposites before we add, so that the equation that results when we add the sides of the equations only has 1 variable in it. Okay. So hence we get the name elimination method, because we're going to set up the system and do something mathematically legal to the system that will eliminate a variable for us. So instead of having 2 equations and 2 variables, we'll end up with 1 equation with 1 variable. So example 1 says to solve the system. And so if we look at our system, we've got variables x and y. So to solve the system means to find all the ordered pairs x comma y that make both equations true. Okay, so again, we need to know what we're being asked to do. So again, we've got 2 variables in our system, so we're finding ordered pairs that make both of these equations true. I guess we're just going to draw an arrow there. So to solve this system, we need to find all x, y, all ordered pairs that make both equations true at the same time. So in this particular system, we're asked what happens on this one if we add the left sides of the equation together and the right sides of the equation together. And do we get an equation that's easier to solve? Okay, so here we're going to take 3x plus 2y and add to that our negative 3x plus 5y. And if this ordered pair actually makes this equation true, then 3x plus 2y is the same thing as 9. So 3x plus 2y, we're going to replace that with 9. And if we find an ordered pair that makes this equation true, then negative 3x plus 5y must be equal to 12. So we're going to replace this with the number 12. Okay, so these two quantities are equal, these two quantities are equal. Therefore, their sums need to be equal. Okay, so on this side now, we have a positive 3x. Okay, so no sign, so that's positive. And in here we have a negative 3x. Okay, so positive 3x, negative 3x, we get 0x. So we'll write that as an extra step here. Okay, some of you probably don't need to write that. And then we've got 2y, and we're going to add to that another 5y. So we get plus 7y. And 9 plus 12, we get 21. Okay. 0 times x is just 0 plus 7y. So this is just 7y equals 21. So to get y by itself, we would divide both sides by 7 and get y equals 3. So now if we go back up, and again, this is where it's important to know what we've been asked to do. So to solve the system, we need to find an ordered pair that makes both equations true. Okay, currently we don't have an ordered pair. We just have y equals 3. Okay, so let's take a look at the first equation. And let's see what happens when we plug in y equal to 3. So again, we're going to put parentheses around our variables before we substitute. So we're going to get 3x in this case, plus 2 times 3 equals 9. So 3x plus 6 equals 9. Subtract 6 from both sides. We'll get 3x equals 3. And if we divide both sides by 3, we get x equals 1. Okay, but what happens if we had used the other equation? So negative 3 times x plus 5 times y equals 12. Okay. So now if we plug y equal 3 in for y here, we get negative 3x plus 5 times 3 equals 12. Negative 3x plus 15 equals 12. And if we subtract 15 from both sides, we get negative 3x equals negative 3. Dividing both sides by negative 3, we get x equals 1. Okay, so either way, since we're finding this ordered pair that makes both equations true, it doesn't matter whether we take this y equal 3 and substitute in the first equation, or if we substitute in the second equation. Either way, we get the same thing. So the same no matter which equation you use. So you can plug it into both just as a double check on your work, or you can plug it into one and have faith that your math is correct. So in here, we're after an ordered pair. So x comma y, so 1, comma, and 3. So this ordered pair is the solution to our system, according to the math we've done, but we can verify that by actually plugging it into both equations. So again, if we start with our 3x plus 2y equals 9, and substitute 1 for x and 3 for y, we get 3 times 1 is 3, 2 times 3 is 6, and 3 plus 6 is 9. So 9 does equal 9. So that ordered pair makes the first equation true. And if we check our second equation, negative 3 times x plus 5 times y equals 12. And again, if we substitute 1 for x and 3 for y, we get negative 3 plus 15 equals 12. 12 does equal 12. So that point also makes our second equation true. So this point makes both equations in our system true, so it has to be the solution to the entire system. Okay, so since 1 comma 3 as an ordered pair, so parentheses, makes all of the equations in the system true, 1 comma 3 is a solution to this system of equations. So if we were to think about graphing these two, this would be our intersection point if we tie back to one of the concepts that we had in the last section. So if we graphed these equations, they would intersect, the graphs would intersect at the point 1, 3.